Hello, everybody, and welcome to this episode of Future Space Economy brought to you by Via Satellite. My name is Jeffrey Hill, Executive Editor of Via Satellite and Executive Chair of the Satellite Show. Thank you so much for being with us. For those of you in the United States, I hope you had a wonderful Thanksgiving holiday. Thank you so much for joining us on the Monday after. Future Space Economy is generously sponsored by MDA Space, a trusted space mission partner to the rapidly expanding global space industry for more than 50 years. We appreciate their support of this webcast throughout the year. We very much appreciate that support. Today's episode is titled Quantum is Coming. How does it change the game for space systems and networks? We just wrapped up the CyberSat event a couple of weeks ago. I was there at the tech track and we heard a lot about quantum computing. When is quantum coming? And in this episode of Future Space Economy, we're going to drill down deep on the arrival of quantum and what that quantum computing and what that means for the space industry. We'll learn about what that arrival looks like, understand quantum computing and quantum technologies, quantum encryption, also applications, the associated risks, and what quantum computing could accomplish in space if these powerful systems are able to survive the harsh environment. We're joined by two very special guest speakers. Before I introduce them to you, I do want to invite all of you to take part of this conversation and submit questions to us throughout the entire hour. We want to answer those questions for you. We know there are a lot of questions around quantum. You could submit questions to us anytime by using the Q&A tab on the right-hand side of our interface here. You can send questions to me. I will facilitate the Q&A. I'll ask your question for you. I won't identify who you are or your company's name. So feel free to ask the questions that you have. We'll get to as many of those as we can in the hour. If we don't answer your questions, we'll take the questions we don't answer and our speakers will answer those offline for you if they can. So we'll open up that conversation in just a moment. But I want to now finally introduce the speakers we have today. First, we have Frank Backus. He's the CEO of Capella Space. He previously served as Senior Vice President for Kratos Space Federal and Commercial Cyber and has spent more than 30 years in the satellite launch, command, control, and communications industries. He is a technology pioneer in the systematic and continuous application of cybersecurity solutions for space systems. You probably know him as the founder, president of Space ISAC, and also serves on the board of technologies for modern technology solutions. Frank, thank you so much for being here with us. First, tell us about your work now with Capella and also what brings you to the table here for a conversation about quantum.
Well, I mean, interestingly enough, right, the world of quantum engaging in space applications and aerospace is coming together for us in a very real way with IonQ's acquisition of Capella. We are now a quantum company and focus very much on quantum compute, quantum networking, and quantum sensing. My new title going forward will be President of Quantum Infrastructure. And basically what that means is the application, the deployment of quantum solutions, both on the ground in the form of quantum, algorithms and quantum processing on quantum computers, but also in the networking space from a secure communications architecture standpoint, and now moving into quantum sensing and quantum P&T solutions. All of those are now under that same umbrella. So the merger between quantum and space is very natural. And I'm going to say it's starting here first.
Excellent. Thank you so much, Frank. We'll talk more a little bit about what you're doing at Capella with quantum computing. Great. We also have with us Dr. Joseph Touch. He's the principal scientist of the Information Systems and Cyber Division at Aerospace Corporation. He supports a variety of projects, including quantum key distribution, QKD, proliferated low Earth orbit, networking, MIL-SATCOM networking, and ground systems architectures. He is an ACM distinguished scientist and a senior member of the IEEE and OSA, has helped publish more than 150 papers on virtual network architecture, internet protocols, nonlinear optical computing, and quantum networking. So, Joe, thank you so much for being with us. Tell us a little bit about your work and your research in this area and what you're doing at Aerospace.
Thank you, Jeffrey. Very happy to be here. So I've been working in quantum kinds of networking things for a very long time. I previously was faculty at the University of Southern California, where I started work on quantum networking with a collaborator in Japan named Rob Van Meter, who's been very influential in the space. When I came to Aerospace Corporation about 8 years ago, I started to help them with quantum key distribution prototype efforts, with understanding the impact of quantum on space. I am first and foremost a networking specialist, but I also have a lot of background in distributed systems, so I do a lot of advising across the whole enterprise. Aerospace Corporation is a federally funded research and development center that advises the United States government on different aspects of technology, and aerospace is obviously focused on space. And so space is what we do and space is what we focus on. So trying to understand that, trying to communicate that, understanding both the capabilities and in a lot of ways, the limitations and constraints of these technologies as well.
Excellent. Well, we have two clear experts in the field, and I already see that we're already starting to get audience questions. That's great. We have a lot to talk about in the hour, so we'll get right to it. Frank, Joe, the first thing I want to do is I want to define the terms here. And the scope of what we're going to be talking about today, because we use terms like quantum. You're hearing it like it's a brand new thing. And for those like me who don't understand this technology completely, can you provide a brief overview of the history of when we say quantum technology in the space industry and what we're referring to specifically when we're saying quantum computing? Who wants to take a first stab at that? Joe, go ahead.
That. Yep. Yeah. So quantum literally means chunk. That's all it means. It means that the information that you get comes in chunks instead of as a continuous thing. So if you think of integers, those are quantum. If you think of real numbers, those are continuous. The quantum properties started off being understood by Einstein with his first papers on Brownian motion and on the photovoltaic effect in particular. So that's how far back it goes. Every time you use a laser, every time you see an LED, every time you use a transistor or a computer, that's all using quantum technologies. So the idea that things have discrete power levels or energy levels in them and things jump between them, that's how we make lasers, that's quantum. Now there's two kinds of quantum that people breaking things into. Quantum 1.0, which is the one that we've understood for over 100 years. And quantum 2.0, which is the spooky action at a distance, Schrodinger's cat, all the stuff that sounds like magic if you explain it right. That's the stuff that is quantum 2.0. Quantum computing relies on 2.0 technology. Quantum 1.0 is what makes your LEDs turn green instead of red, or everything else that we know, fluorescent lights, things like that. What we hope is that we can do things with quantum technologies that we can't do with conventional technologies. And that is a very important distinction. One of the very, very short ways I explain this to people is quantum computers are like starships. They're really good for going to another planet in another galaxy, and they're crap for going to Target. Okay, it's just not going to get you around the corner to pick up groceries. You need a Corolla for that. And just like the starships that you see on TV, and in the movies, often need a shuttle or a Land Rover when they get there. Quantum computers can't exist without classical ones. Quantum communication can't exist without classical. So that's what we're talking about, is these technologies that use these new capabilities that sound like magic if you explain them right, in ways that are almost fantastical in terms of the capabilities that they can support.
That was a great overview of the history. Frank, tell us about when Joe is talking about quantum 2.0 and explaining it the right way so it sounds like it can do magical things. Like, what is the physical manifestation of quantum 2.0? Like, what is it that people say is coming?
Well, to give you an idea, and of course, I've been in my career for over 40 years. So even going all the way back to 40 years ago, in order for me to get my degree in semiconductor physics, the foundation classes that were required were quantum mechanics. So understanding the fundamentals of, the atom and ions and those types of things. And what we're talking about is using those fundamentals to be able to generate the quantum technologies that we're talking about. In the case of quantum computing, the ability to affect an ion, both from a measurement perspective, right, and a setting, I'm going to say the value of the ion, to use it somewhat, and I use this very loosely, to use a single ion in a way that is similar to the way we would think of a transistor today. And those are core fundamentals that allow us to then do computing at a dramatically faster pace, in a dramatically smaller form factor, using dramatically less power. I mean, we've all talked about artificial intelligence limitations that are relative today to the power consumption of the data centers necessary for these incredibly high-end artificial intelligence large language models. We're talking about data centers now, putting in their own nuclear power plant or their own power infrastructure to support the data center. In the quantum world, we're talking about orders of magnitude less power from a power consumption standpoint, but dramatically more performance capability. Now, with that comes a different way of doing computing. So the standard compilers that you are familiar with today, and the way that you write the code and the way that you create your algorithms are fundamentally different in a quantum environment and in a quantum space. And that technology is maturing dramatically right now. The other one, right, is this ability to measure the impact of the environment on a single ion. So in other words, being able to do, a gravity-based measurement sensor to determine your location on Earth instead of using traditional, GPS, PNT. If we have the ability to measure at the quantum level, we have the ability to create a sensor that can give us dead reckoning-based navigation, even at the bottom of the ocean. So it's a very interesting scenario to be able to apply quantum sensors from a navigation standpoint, from the bottom of the ocean, right, to a terrestrial, to airborne, all the way up into space. But those are the technologies that we're starting to see on the sensing side. Those are probably the most mature of the quantum technologies in the market today. We see them with a company like Vector Atomic, who IonQ acquired on October 2nd, where we are now looking at quantum clocks that are being manufactured, delivered to the community. But there's fundamental changes going on now in these quantum levels. But really what it comes down to is the ability to measure at the atomic level and be able to affect the state of an atomic component like an ion, and be able to do it in a predictable way. Okay, and then the key is be able to now, can I move that environment? As Joe said, I can't move, I'm not going to go down to Target with a Starship, right? I'm looking for a Corolla. Well, really what we're looking at in the quantum industry is how do we package these things in ways that can operate in predictable ways, right? In smaller packages, under the ocean, terrestrially, in atmosphere, and up into space. And that maturity of these technologies is what we're seeing accelerating at an incredible rate today.
So just the reduction of power requirements is like a dream for the satellite and space industry, right?
Well,
so no wonder
I'm gonna push back on that a little.
Joe's going to push back on that a little bit. So let's
yeah, I'm going to push back.
This is good. This is good. So, I'm going to hear it.
A quantum computer inherently operates at very, very low power because it's very much like playing with a bunch of dominoes that you just tip over and boom, they all just go boom. That's the whole thing about it is, and that's one of the reasons they're great for sensing, is because they react to everything in the environment. That's also their downfall, is they react to everything in the environment, which means you have to isolate them. You have to refrigerate them. You have to isolate them magnetically. These things take power. The quantum computer at USC takes power equivalent to running the whole of the rest of the USC, or ISI rather, in terms of it consumes an immense amount of power. Now, the quantum computer at its core is this little tiny chip that uses almost no power at all. Right? It's all the supporting electronics, however, are immense, including a computer that would dwarf most of the computer we use for almost any other computing. Quantum computers can't exist without a classical computer sitting next to them that generates a lot of heat and consumes a lot of power. So that's the first thing. The second thing I think Frank brought up a very interesting point was, again, because they react so well to things in the environment, they're inherently suited at sensing, and that's a great thing. Okay, for timing, for detecting things, for all sorts of like radars and stuff like that. But it also means a quantum computer doesn't give you an answer. It might give you an answer, and then you run it again. And it might give you a wrong answer, and you have to run it again. And you can tell the difference between a right answer and a wrong answer. But the thing is that because it is internally, think of it as all of these dominoes on the knife's edge of tipping over. Any sort of influences at all will make it do the wrong thing. And so that's part of the challenge of adopting these technologies and using them reliably is, where do we benefit from that inherent fragility, and where does it become a problem? And again, the power problem is significant. It's they talk about using quantum computers in space. Well, space is a harsh environment. I cannot take a cell phone and put it in space and expect it to run. It'll run for anywhere between a couple of days, a couple of months, depending upon how high I launch it. And if I put that thing, at geo orbits, it's not going to last very long at all. It's going to get fried. That interaction with the environment is something that will mess up the quantum computers a lot. And so we don't know how to. It's hard to build a quantum computer on the ground. They're inherently big, heavy, bulky in terms of the supporting electronics. Right? That's the issue.
Yeah, and so architecturally, what we're going to see in the near future is changes to fundamental algorithms that will allow us to operate algorithms in a hybrid environment, traditional CPUs, GPUs, and quantum computers, to be able to achieve much more, I'm going to say, performance for certain types of applications. And we're going to see quantum computers in that environment. I don't necessarily expect a quantum computer to be on a satellite in the immediate near future. However, being able to interconnect via optical interlinks a sensor on a satellite to a quantum processing capability is going to be an important transformation of the way that we process quantum sensing. So it's going to be interesting to see how the maturity of these technologies go forward. One of the things that we did recently over the last 45 days was acquire Skyloom, which is a high performance optical terminal company, so that we will be able to do quantum entanglement and quantum entanglement exchange between quantum sensors and quantum computers. And the whole point there is to be able to stay in the quantum space across the capability for as long as possible before we have to go into traditional mediums for the sensing and for that processing. But again, there's maturity that needs to be done in that environment. And the opportunity we have in the industry right now is to mature these technologies, I'm going to say, that have been maturing in decade type timelines, and start maturing them in years and months. In other words, the cycle time for the maturity and the stability that Joe is talking about is going to accelerate dramatically now with, I'm going to say, proper investment into these technologies and being able to bring them together, being able to bring quantum computing, networking, sensing, and the optics necessary all together in vertical architectures, so that we can, again, take advantage of what we know quantum is, as capable, of being capable of doing.
So yeah, you mentioned that the quantum stuff, the quantum algorithms. I think that's a very important point. A classical computer, that's what we call a regular computer, right, is good at a bunch of algorithms. We all know what they're good at. They sort numbers. They're good for searching. They're good for certain things. They're really not good for certain kinds of problems. One of them is called the traveling salesman problem, minimization, finding things in a big search space, the kinds of things that we throw the AI at today. Obviously, classical computers are not really good at. Quantum computers are. Okay, quantum computers are also good at the kind of math that is behind a Rubik's Cube. It's called abelian groups. And that particular kind of math is also the kind of math that can break some of the cryptological algorithms that we've been using for a very long time. It's why we have to have post-quantum cryptography that uses new algorithms that doesn't rely on that math, relies on other math to secure things. Now, the thing is that a quantum computer, like that Starship, it's not going to sort 3,000 numbers faster. It doesn't do that. The things that a quantum computer does are very distinct, and we have to make sure that we're using them in the right way so that we can leverage their capabilities to their fullest.
Okay, this is good table setting because I feel like I already have a better understanding of what we're talking about, the scope of when we say quantum computing, what we're talking about. And as you mentioned, we have very specific quantum applications that are already happening and have been happening. We have a long history with it. But what we're talking about, the big change that you're talking about is this sort of fundamental change in computing. And so we'll get to that. But, we have some audience questions. I want to get to those. The one I want to ask right off the top, because it's always the most popular, is the question, when is it going to get here? But I don't want to just throw out a date because that's meaningless, right? Instead of that, I want to ask, what does an arrival look like? Like, what are the steps? What are we going to see in the research arena? What are we going to see in the product development? Like, what does adoption of quantum look like? What are some key stepping stones, I think, toward that it's here moment?
Yeah, let me jump in on that, Jeff, and then Joe can counter kind of where this sits from my perspective. Because the seat I sit in as the president of quantum infrastructure for IonQ, and the CEO of Capella Space, right, is the actual implementation of these technologies and using them in known value, and value chain or economic ways. So as an example, deploying a quantum clock that is dramatically more reliable, higher fidelity than the GPS clock that I use today. So as Capella Space, we use a GPS-based clock and timing architecture in our proliferated LEO constellation. The problem is when we're over certain areas of the Earth, we're getting GPS interference that are affecting the reliability of that clock, which affects the quality of our data from an Earth observation perspective. So the first and most direct impact for us is going to be flying our own clock and doing that with a quantum clock that has as high a fidelity and, quite frankly, dramatically higher fidelity than the current GPS clocks that we're using today. And being able to do them at a swap, size, weight, and power, that can fly on our satellites. Because if I can resolve my issues with dependency on GPS that is inherently impacted by interference and spoofing, and move to an architecture that is not impacted by interference and spoofing, the quality of everything that I'm doing on orbit will get better. So that, by the way, that mission to fly those clocks is being planned in 2026 and planned for launch in 2027. And there's already some of this technology with Vector Atomics on orbit today. So it is definitely in our near future. We need to get it to a size that can go on a traditional LEO, low Earth orbiting satellite, which we know what that looks like, and we know what the timing of that is. And the mission is being planned as we speak to deploy that capability. So that's one example that I'm going to say is very specific, has a very specific impact that everybody in low Earth orbit are currently dealing with, which is GPS interference and GPS spoofing. So over to you, Joe, on a timeline of something, I'm going to say very specific.
Okay, so I'm going to quote people again today. Isaac Asimov said technology is sufficiently advanced when it is indistinguishable from magic. Okay, and my measure for when a technology has arrived is when it fades into the background. Okay, 20, 30 years ago, we would all marvel at how fast we could set up a dial-up modem. We don't even think about that anymore. It just is there. The internet's there. 150 years ago, people marveled at the idea of turning a light on with a switch. We don't think about that. It's just there. Okay. So quantum computing will have arrived. When we don't think about it, it's just there. And as far as I'm concerned, I appreciate the idea of using it as a replacement for GPS because GPS is a massive target of attack, right? It's a big central system, it's a coordinated system that everybody would love to. Hey, let's attack it, right? But I also think that if for anti-spoofing, the quantum stuff's great, but for attack resistance, it's again, it's knife's edge, fiddly stuff that if you really wanted to mess it up, it's too easy. However, I do appreciate using it for clocks. That's not going to be the thing that's going to change people's minds about it or be that dramatic shift. To me, I'll tell you, when UPS and FedEx use it to plan their routes, when quantum computers become the kind of commercial service that AWS is, you take your problem to them, and big companies are going to take big problems like planning routes, like things like that, to them and say, can you optimize this for me? And they're going to come back with a better solution than classical computers have had. That's when it'll have arrived. That's my metric.
Yeah. And a good example of that, Jeff, in the space world, right, is a problem set that we live every day in the space world. And that is the constellation planning and communication planning for ground stations to talk to satellites. That problem set, right, is owned in the NASA world on one side and owned at 22 SOPs, right, in the Space Force side of the equation. I've worked on this problem set for decades. And quite frankly, one of the most effective algorithms that I've ever deployed for that problem set was a genetic algorithm to analyze all the possible permutations of the schedule, and then be able to put out an efficient schedule for that entire set of ground stations and satellites. It's the number of permutations that are possible are in the millions, and you want to be able to make these decisions almost in a continuous way. And the nice part about quantum computing, as an example, is those kinds of algorithms, like genetic algorithms, run very effectively in a quantum algorithm type environment. So I anticipate being able to deploy a genetic algorithm on a quantum computer to optimize a complex schedule like Joe was just talking about, an AWS, delivery trucking, algorithm across the entire continent, or all of our satellite communication interlinks. These are complex problems that need to be solved on a continuous basis. And those kinds of algorithms chew up a tremendous amount of traditional compute and GPU-based compute today that I think are going to be the easier kinds of algorithms for quantum in the near future. And so those very specialized types of algorithms running on a quantum computer, I envision that, in the next 2 to 5 years, from a timeline perspective.
Okay, and that's that's a very clever compass to use, is when quantum is here, when it's being used for logistics and transportation, because that truly is the background, right? That's when it's running automatically, and nobody. Well, that puts a lot of pressure on UPS, but we'll check on UPS to see when they're using quantum for route planning. All right, I want to get into some of these questions because a lot of the questions from the audience are, can quantum do this? So the first one is, how long until quantum state teleportation can be used to reduce ping times across very long distances?
That's never going to happen. What you need to understand is you can't beat the speed of light. Everybody talks about it. Nobody ever does anything about it. You can't beat the speed of light. Quantum communication does not travel faster than light. So when you talk about that quantum collapse, when you talk about the I pick one thing, you pick another thing, you cannot use it for what's called information transfer. And the reason is that you and I can hold a quantum entangled state together, that the state's entangled between you and I. And you can collapse it down. And whenever I look at mine, it will match yours, even if I look at mine before yours, which is kind of weird. Okay. And that's that spooky action at a distance. But the one thing we can't do is control which way it flips. We can't force it to be heads or force it to be tails. At that point, it might as well be a coin flip. Because it's a coin flip, you can't use it to communicate information. So no, doesn't beat the speed of light. No magic there at all. What it can do is it can make things match that are not under their control. And this is a big thing about quantum key distribution. Quantum key distribution is one of the most misnamed technologies on the planet. Yep. Quantum key distribution is not distributing anything. It doesn't distribute a key. What it does is you throw things at me, I throw things at you, we both do some math, and we both compute the same thing. That's what it does. It's distributed quantum key generation.
There you go.
So that's the key to understanding it.
That's right. And those keys are compatible with each other at distance.
Yeah, the your key matches my key, but we have no control over the key at all. That's part of the good part about it, is we have no control over the key, right? But because you have no control over the key, it doesn't happen any faster. Number one. Number two, all those things we threw at each other, guess what? Speed of light.
Yep.
Everything's speed of light. The only other things that we can throw at each other that will actually go the distance between you and I are gravity particles. If you watched Interstellar, you can understand that using gravity as a mode of communication will work too. Speed of light. You move the moon, it will take a few seconds for it to change the Earth's tides. It's not going to happen instantaneously. It's the same thing.
I think this is the second part of a two-part question. So we've heard a lot about quantum state teleportation happening over the light spectrum over a significant distance. Can the same be done over the RF spectrum?
Well, light is RF.
Right.
Light, they're just different frequencies. And yes, it's absolutely.
Now, in our world, in a traditional infrastructure deployment state, the ability to use optics for entanglement of the quantum state that allows us to share keys, we can then use those keys for encrypting RF traffic. So we're not moving the keys over traditional RF, but we are using the keys to be able to encrypt that traffic. And so it's in a hybrid architecture, secure communications environment, that type of key management, as opposed to key distribution, I'm going to say is going to improve the reliability of the security of RF communications dramatically. And I think we're going to start to see those deployments very soon. We're seeing them today, driven very heavily in the banking world. They're doing a lot of research and a lot of work in terrestrial fiber. But those encryption architectures will continue to expand. There's no question that they will be more secure than, let's say, RSA 2048. But the reality of the situation, from my perspective, right, is a implementation of those capabilities that, again, are reliable, useful, become part of our traditional infrastructure.
So I want to circle back to two things. First of all, using optics versus using RF to exchange quantum state. And the reason we use optics is because if you want to think of it this way, if you remember high school physics, everything is both a particle and a wave. Okay, but when it's a particle, it's the size of the wave. And so when we send light particles, they're very, very small, very short, millionths of an inch. And so the chance that something will fly past it or interact with it is very, very small. When you send radio waves, they can be a football field long. And so although you can use them for quantum exchanges, and they do travel exactly the same speed of light, they're both radio frequency, they're just different frequency. The optics is a lot more efficient because you can send a lot more of them in a given piece of time than the radio waves ones. That's the first part. Second part, as Frank said, we exchange these keys to do classical encryption. Now, I'm not completely sold on that. I think the banks use quantum encryption the same reason they'll tell you that they use a quantum computer today, and that's because it's good advertising to say they do quantum. I'm not completely sure they don't buy quantum equipment and put it in the closet and turn it off, just so they can say, we bought all this quantum equipment, so we're part of the future, but they don't actually use it. It is still way more effective to exchange keys using other methods, unless you think they're going to be attacked. It's way more efficient to use a sneaker net, as they call it, put them on a thumb drive, move them around. It's way more efficient to exchange them with other means. The question is, what kind of attacks are you under, and how persistent are the attacks, and how often do you change the keys? And if those things don't change from the way we do them today, there isn't going to be a need for quantum key distribution. So right now, a lot of the rules about how long we use a key are based on, well, how many keys can you get in a day, right? They're not designed for quantum key distribution, but even quantum key distribution today doesn't distribute keys all that fast. It might take tens of minutes to exchange one key. So yeah, I take all of this with a grain of salt when banks say they're using it. They just want to be part of they want to be they want to be on the show, as they say in Galaxy Quest, right? They're just jazzed to be on the show, so they'll say quantum this, quantum that.
Now, Joe, you actually started answering the next question here, very popular one, which is probably what most people associate quantum computing with, are security issues. The question from the audience is, how will quantum computing affect the security of today's encryption? What can our organizations do to stay quantum safe? I'm going to add something to this. I'm going to say, what can they do now? And then what can they do when UPS is using it for logistics and transportation?
Yeah. Let me kick off with, the first component, right, is, when are the quantum computers going to be able to start to break traditional encryption systems that we're dependent on today? And from a space perspective, one of the most typical encryption infrastructures in the commercial space industry today is just AES 256. It's used for a lot of the command and control of a lot of spacecraft from many companies. The challenge is that technology relative to the encryption will be broken first, before RSA 1024, before RSA 2048. And so the space world, and this is part of my work with the Space ISAC, is to start to move forward with security architectures that are going to protect our space systems and the purpose of those space systems much more effectively than what is available today. And I would say, in my research and the work that IonQ is doing, we anticipate something like AES 256 to be the first encryption technology to be vulnerable to quantum computers. And there could be an argument about when that is, and the when might be 2 years, it might be 5 years. I don't think it's 10 years for something like AES 256. And then the question becomes, when does RSA 1024 and 2048 start to become a risk? And our job from a security design perspective, right, is to start deploying security architectures that are not vulnerable to these risks. And as an example, when a nation state adversary has the ability to break those kinds of encryption in a timeline that is relevant to the data that they're consuming, they're not going to advertise to the rest of the world that they can break our encryption. It's just like, back in World War II, when we, broke the encryption, right, of the adversary, we didn't advertise on a global basis that we're breaking their encryption. We wanted them to continue using it for as long as possible so that we could then break that encryption to our advantage. I think the same is going to occur going forward with quantum computers. The encryption is going to be broken long before people are aware of it. And it is our job, right, to lean in and lean forward into more secure architectures. And it's just a question of, is it post-quantum encryption or actual quantum encryption? The reality is layering these technologies on our systems going forward are going to be important for us to do, because there's no question we have to move beyond AES 256, RSA 1024, and RSA 2048. Those are the core encryption infrastructure of the internet, of most of our space systems. And clearly, national technical means space systems have more sophisticated security today, but people are still concerned about when a quantum computer is going to be able to break it.
Right, but you got to put this in perspective. First of all, AES is what's called a symmetric key. Use the same key to encrypt as to decrypt. In a quantum computer, the algorithms that we know today, and that's all we have right now. It's not like we've come up with dozens of new algorithms every week. The only algorithm we've ever found for cracking keys, for symmetric keys, reduces the size of the search space by half. So it makes the key half as long as it would have been. So instead of a 1,000-bit key, now you're working with a 500-bit key. If somebody were to crack that key that I used 3 months ago to command my satellite, that's not going to have any effect today because I'm not using that key anymore. They have to crack it while I'm using it. Okay. When we talk about some of the technologies like IPsec, which is a tunneling technology that we use to encrypt things, that uses a key to identify the endpoints, and it is only susceptible during that exchange. And then after that exchange, the question is, when is it susceptible? So not all algorithms are susceptible the entire time you're using the key. Some of them are only susceptible in that initial exchange period and things like that. I worry much more about the asymmetric key systems, the RSA, the public key cryptography, the one that says you have a public key and a private key. Those are the ones I think are more likely to be attacked than other things, but we're replacing them with new things. I do worry personally, individually. I worry about the fact that we are rushing to replace something we think could be cracked with something with a set of algorithms that have been cracked on a weekly basis practically. There were dozens of candidate algorithms to this that I thought, here's this 20, 30 algorithms that are up for consideration. And, while we're looking at the screen, things are, okay, no, don't use that one. It's been cracked. Don't use that one. It's been cracked. Don't use that one. It's been cracked. I would be much more comfortable personally if we left AES and RSA in place and encrypted on top of that with something else, than to replace it with something that we don't have 20, 30 years of experience with. Okay. I love the idea of layered encryption, layered defenses. I don't want the adversary to be able to throw encrypted streams at me at very high rate and have me have to burn a lot of power and swap decrypting things that are junk. I want to have a triage level that I can apply to the incoming traffic. These are the things that I don't personally think we're doing the right thing for in terms of future proofing and quantum proofing our algorithms. I would prefer we built things with layers of encryption, layers of experience with that encryption. And as we dabble into these new kinds of encryption, we add them to what we're doing rather than swap them out. But when is that going to happen? I don't know. I absolutely believe what Frank said. If you watched The Imitation Game, fantastic movie to understand two things. Number one, Alan Turing's contribution to computer science as a whole. But second, people don't understand his contributions to game theory. His contributions to game theory came out of how many things can I crack and act on and not give away the fact that I have your keys, okay? Because if I give away the fact that I have your keys, what's the first thing you're going to do? Change your algorithm. And then my method isn't going to work. That's a big deal here. And in some sense, I wonder when we're going to when we're going to start thinking about using the quantum computer to think about that part of the problem, to think about the gaming problem rather than just the cryptography problem. Worried about, when we find a way of doing something, how do we know what to do so that somebody can't notice it? We talked about quantum detection and quantum radars and quantum sensing. One of the kinds of quantum sensing that's really interesting is the idea that you can actually sense whether something's there even when particles don't come back to you. Okay, that's almost like a stealth sensing. that the attacker doesn't even know you're sensing them, and you know they're there. And that's where it gets fascinating to me. I think that's where the opportunity lies, to use these technologies in a very new way.
Thanks, Joe. Frank, before we move on, do you share some of those worries with Joe, or do you have a different view on when he said he worries about replacing algorithms with others that have already been cracked, or looking for a security solution that is already obsolete?
Well, I mean, 2 points from my perspective. One, it's always been about a defense in depth architecture. So it's not, and by the way, it can't only rely on encryption, right? So a defense in depth architecture relies on many things. Encryption happens to be one of them. And so it's important. And then from an encryption perspective, right, there's bulk encryption, right? There's layered encryption. We use it today. I mean, as an example, the way that banks exchange transactions today, right, uses layered encryption in order to move data around the planet and to move those transactions. And so it isn't just one encryption that a bank is using to protect its information. One of the challenges is that we believe that adversaries are recording information in order to break that encryption at some point in the future. And so you look at data at rest, right, and the ability for somebody to record what was transmitted, break that encryption at some point in the future, and be able to see that data. Now, if that data is still valuable in the future, then it could be a problem. But the data needs to actually be valuable in the future in order for it to be important. So changing things like, and really one of the biggest threats to the whole security architecture that people deploy today are really their own passwords, right? I mean, again, from a defense in depth perspective, the number one password used in the world is 1234556. Okay, that's not exactly the most secure password. And basically what people are doing is giving up, right, one layer of defense by not using proper passwords. Now, personally, I can't stand passwords because I got to manage hundreds of passwords, which then makes me use a password system. And, all of a sudden there's a nightmare there. So to me, it's about defense in depth without question. What quantum brings us is another layer of defense that we can bring into our traditional architectures. And I think that's an important thing for us to be doing, is to look at another layer that is available to us to protect our most secure systems. I don't anticipate somebody necessarily, using quantum encryption for all of the, I'm going to say email traffic that they do on a daily basis. Mm-hmm. But if I'm trying to send very critical information between two, core systems of national security, the approach to security is going to have multiple layers of depth presented to them. And for me, in the commercial satellite or commercial space environment, we don't always have access to things like national technical means security systems. They don't make them available to us to put into our systems. And so we, from a commercial perspective, need to develop much more secure architectures for protecting our commercial space infrastructure.
Right. One of the things we didn't talk about with the quantum key systems is the quantum key generation, I'll call it generation algorithm, distributed quantum key generation algorithm. What it does is it distributes a key that at the time you distribute the key, with very high confidence whether or not somebody else has a copy of that key or not. Now, once you have that key, if you just write it on a piece of paper and put it on a Post-it on your monitor, it's no good, right? It's no good than anything else. But the place it gets interesting to me is not using them in classical algorithms. It's using them in a particular classical algorithm. One-time pad. If you can generate quantum keys at the data rate that you need to use the key in a one-time pad, which is the same rate as the data you're sending, then no one ever, if you've done the exchange, and at that exchange you say, oh, nobody knows that key, as long as you don't write that key down anywhere, the data is protected forever. It cannot be decrypted with a quantum computer. And that's important because, and the reason why, it's a real subtle reason. I'll tell you a really quick way of thinking about it. The way to think about a one-time pad is that everything that is the same length as the thing you encrypt is a valid way to decrypt something from a one-time pad. So if I give you 5 pages from the beginning of War and Peace and encrypt them, under a different key, it will decrypt to the first 5 pages of every other book on the planet. So you can't just go, oh, wait a minute, it came out as English, that must be the right key. No, that's the way we crack. That's one of the ways we find that we cracked a key, is it starts looking readable. And if it can be everything that's readable, it's nothing. So you don't know. And that's part of the issue here. Yeah, so I don't know when we're going to get there. But as Frank said, there are some interesting things here. There is some layering opportunities. There are some resistance opportunities. It's all part of the bigger picture of when are we going to be able to use this technology and how we're going to be deploying it. But I think the key other thing that you should get out of this conversation is quantum key distribution, quantum computing, improved sensing with quantum sensing, right? These are related because they use the word quantum, and that's almost all that they're related in. They have almost nothing to do with each other, although you can use a quantum computer to deal with quantum sensing, processing quantum sensing remotely. A quantum computer isn't a quantum sensor, and a quantum sensor isn't a quantum computer. And so these are sort of different realms that have to be solved if we're going to look at that bigger picture. And it is vast, the territory that these cover.
Yeah. And going back to one of Joe's very early comments, right? When this becomes commonplace, in other words, infrastructure, right, is when we know we've really made the leap, right?
Yeah.
From that perspective. And the steps, there's no question from my perspective, what we're seeing in the world today in all 3 areas that Joe just mentioned, right, is dramatic advancement, dramatic investment, right, to mature these technologies into reliable, deployable, and economic models that make sense.
Yeah.
And without that effort, right, we'd still be looking at decades into the future. But now with that focus, one of the things that is common across all 3, right, is the physics related to using quantum technology in these different ways.
Yeah.
And the knowledge, the experience, right, and the maturity of those is moving very quickly right now on a global scale. And so I do anticipate, right, I'm going to say hockey stick kind of approach to the maturity piece. Now, in the process of maturity is going to be us learning how we're going to deploy these technologies from an infrastructure perspective.
Yeah.
They're not going to work in every single place that people are considering today. And quite frankly, they might work in certain models that nobody even thinks is possible. But that's the excitement in quantum right now, is the opportunity for us, I'm going to say on a global scale, to be maturing technology that nobody knew anything about before. And I'm talking about quantum 2.0 world, right? I mean, before the transistor existed, okay, there was a whole different world in the way we did electronics. So I'm going to say post-quantum is going to be a whole different way, and on the way that we look at compute and the way that we look at sensing and the way that we look at networking. We don't all know what the outcome is going to be yet, but we do know that the maturity is accelerating dramatically. The investment is accelerating dramatically. And there have been proven outcomes that we think are going to have economic impact for sure. And certainly,
but before we move on, I do want to we have 5 minutes left. I want to get some questions from the audience, and these we'll try to get some of these out. Yeah. First question here: with video media applications rapidly declining on geo satellites, do you think broad quantum computing capabilities on any orbit satellites may bring revival of satellite media?
I don't think it has to do with quantum. I think it has to do with data transport.
Okay.
And really the difference in media is the transport of the data and the latency relative to the transporting of that data. If latency matters, then low Earth orbiting satellite constellations are going to matter. But in reality, what's going to happen is an interconnectedness between the ground, LEO, GEO, MEO, right? And quite frankly, the ability to transport data at much higher speeds than what we've seen in the past. And quantum might help relative to security, but the core technology here is about data transport speeds.
Mm-hmm.
Yep.
Okay, another question is, how can we apply quantum to software-defined data centers in space? What are the benefits and limitations?
I think that we're going to be using it for optimization of the design of those things, but we're not actually going to move the quantum computing into space.
Okay. All right, next question is the long one. Bear with me here. Think about standard task in interplanetary spaceflight navigation. Integrate the equations of motion for a single spacecraft over millions of integration steps, classical Runge-Kutta into integrator scheme. Can the algorithm for a computing task in this category, which is already optimized for execution on the classical von Neumann type computer, be reformulated to execute much more quickly on a, quote, quantum computing device?
No, it's going to target with a spaceship. It's not going to help you. The thing is that it's not going to run any faster. In fact, if anything, it's going to run slower if you tried to do it. What you need to compute is you need to compute on something that is either these three categories that we know how to do quantum algorithms for, which is this abelian mathematical group thing, which is rings and groups and fields and things like that, they're called. Okay, it's discrete mathematics. The second one is basically minimization problems, that planning for FedEx or UPS or something like that, or designing these other systems to minimize certain aspects of power or wiring or things like that. And the third one is a quantum computer is a great way to model a quantum system. Now, the flight of a satellite is not a quantum system. It's a classical system. And so all that classical Newtonian mathematics, no, not going to help you at all, unfortunately.
All right. We have a couple of minutes left. This is probably going to be the subject of a separate webcast, because I feel like people are asking, and I know, Frank, you alluded to this earlier, but like, how does the physical infrastructure around quantum computing change? Like when you reach a certain scale, like what, especially on the satellite and space world, how does that change the physical infrastructure? And again, we can do a whole hour on this, but
of course. But the infrastructure component that we're talking about is the ability to interconnect either quantum computers, right, or quantum sensors across a quantum-enabled network, or the exchange of photons. And so what we're going to see, I believe, first is the ability to interconnect quantum sensors across an optical network and use that infrastructure for traditional capabilities. And then moving beyond that, we're going to start seeing quantum sensors that can be deployed into the environment of space, and like an RF sensor, as an example, or a navigation sensor. Some of those are being put on orbit today, and we're seeing some results that are very promising there. Again, with investment, right, and an increased cycle time for maturity of those technologies, that's where I think those changes are going to occur most quickly. And then between quantum computers, when you can interconnect, and the challenge right now is speed, but when you can interconnect two quantum computers and start creating a quantum cluster of computers, what you can do from a processing standpoint starts to become much more interesting. But right, there's work to be done relative to those quantum networks. And right now there's a number of different technical approaches to how you might interconnect quantum computers. But those are the areas of research that are starting to move into operational capability. And we are right now at that transformation, or that tipping point of what's research and what is operationally relevant, and then eventually what is going to become common infrastructure.
So a lot of the things have to change. You can't take two quantum computers and connect them with an internet connection and make a bigger quantum computer.
Yes.
It doesn't work that way. You've got to connect them with a quantum computer.
Yes.
Apple found out that when you build a chip, if you put the memory so close to the CPU that it's not actually communicating, it's actually the communication is such a big thing that putting the two on the same chip had a huge win for the M processors versus having a bus. Okay.
Yes.
And we're learning all these things about how distributed systems are, even inside your computer box, it's a distributed system. All of the things that we know how to do today, all of the laser comm, all of the RF comm, everything that we have has in it something that mucks up quantum in such a way that you can't just use the off-the-shelf stuff that we have today for quantum anything. You have to rebuild it. You can put a mirror in there, but a lens, not so much, not necessarily. Depends on the lens, filters, everything you do. Remember, everything's on a knife edge. And if you touch it the wrong way, it will make it turn back into classical and remove all that magic that you wanted to maintain.
Yep.
So we're going to have to figure out how to put quantum storage, quantum relays, quantum entanglement swapping, purification steps, which are a way of taking a bunch of quantum entanglements at low fidelity, low quality, and turning them back into one at high quality. So you're consuming the system. This is quantum networking. We don't know how to do it. We're just right now at the stage of where the internet was when people realized that, a single transistor could work better than a relay or a tube, right? But we're not at the point where everybody can do AOL at home, right? We're in that in-between phase where it's sort of like, oh yeah, we can see it coming. But, and I want to caution, we saw bubble memories coming. We saw Josephson Johnson's coming. There are things we saw coming. We thought were going to change the world that never panned out. We don't know. We don't know if this is going to work or not going to work. We don't know the amount of money people are putting into it. We don't know. We think it might. We hope it might, but we don't. We really just don't know. And so right now, I don't know what's going to change the future. I know that 10 years from now is going to look different than today. I know that the things that you think are your limitations today aren't going to be your limitations tomorrow. Used to talk about, oh, my dial-up is so slow. If I could just get faster dial-up. I don't know anybody who says, I wish I had faster internet at their house anymore. Turns out a couple hundred megabits is more than enough for most people, right? So there's a point. We stopped buying computers every week because there was a faster processor.
Right.
You just don't need them.
Right.
Okay, why? Because they got fast enough. And when is that going to happen for quantum? I don't know. I don't know if it's going to happen for quantum. With all due respect to Frank and his company and everybody else here, there's not just a when involved in these questions. There's an if, and I don't know the answer to that either.
I will say though this about it, Jeff. Looking at this in comparison to, let's say, the launch industry, right? If we had waited for the traditional approach to advancing launch, okay, as opposed to the approach that SpaceX took, okay, we'd still be launching large satellites on large rockets one at a time, okay? Mm-hmm. But we didn't. Somebody made a choice from an industry investment perspective to do it a different way, okay? IonQ as a company is making a choice to do computing and networking and sensing in a different way going into the future. We're making that choice as an organization. We're making those investments, right, as a company. That's the way that these kinds of things change into the future, is by somebody or some organization making a choice to move in a new direction. Yeah. And so our job, right, is to now make that choice and then move it into this new direction, into an economy that's going to be a return on that investment and that choice. Yeah. There's no question that IonQ, being a pure play quantum technology company, has made the choice, and the advancements and the investments are going to be made from IonQ. And we're going to drive this direction. To Joe's point, not everybody knows what the outcomes are going to be yet. But the one outcome I can guarantee is that the companies who make the choice to do this are going to be the ones who actually make a difference, right? And prove a future using quantum technology as possible. The ones that are waiting won't be the ones that make that choice.
Well, Joe, Frank, thank you both so much. This is extremely educational for me. I hope it was as educational for everybody listening. It's good to we need to know the realities of it, where it is, what steps we're taking with different applications. We did address the security issues around quantum. We talked about some of the physical and computing limitations and challenges, but also the potential for future applications. And in future conversations, we can talk a little bit more in depth on each of those separate conversations. I even think, like, how does hardware change? How does the infrastructure change around it? Is a fascinating conversation to have. And I'm glad we didn't just boil this down to here's when quantum is coming, here, buy this solution and you'll be fine. I hope everybody got more out of that than that. But Joe, Frank, really, thank you so much. This has been a fantastic conversation. Thank you to all of you who participated here. I know we didn't get to every question. We will submit those questions to our speakers. Hopefully they can get back to you offline and answer some of those. We really appreciate it. Once again, my name is Jeffrey Hill, Executive Editor via Satellite, Executive Chair of the Satellite Show. On behalf of my team and I, we thank you for joining us, and we will see you very, very soon for the next technology webcast we have here on Via Satellite. Joe, Frank, thank you so much.
Thank you.
Thank you, everybody.